It's always true. In this case, the one variation we're going to talk about is the lysogenic cycle. The lysogenic cycle. First off, it's identical to the lytic cycle. What we just did is the lytic cycle. And that just means the cell's going to rupture. Now this is the standard operating procedure for viruses. What we're doing now, the lysogenic. I want to tell you though, the stages here are identical to the lytic cycle. So they go through the same stuff: attachment, penetration, biosynthesis, maturation, and then release. It's all the same. Well, clearly something's different, or you wouldn't have a different name for it. Sometimes viruses do not cause the death of the cell when they infect it, when they multiply. They go into a dormant phase. In other words, they'll enter into the cell, they will combine with the host DNA. They'll become part of the DNA. And then they go to sleep. And the term is they become a prophage. A prophage is the host bacterial chromosome plus the viral DNA. So it's all now one big piece of DNA. And again, essentially, the viral DNA is dormant. It falls asleep.
Immediately becomes dormant, or
Yeah,
after
pretty
it-
much, pretty much. Pretty much.
Now, are these just specific viruses that do this, or can any
Lysogenic viruses. Yeah, not all viruses. These are specific lysogenic viruses.
So is this kind of, people can be carriers for things like strep throat and stuff? Is this kind of how that,
It's one possibility.
okay.
I don't want to say every time,
Yeah,
but
but that just means that they have
Definitely
these
a possibility.
prophages in their body for whatever reason?
yes, yes. So each time the host DNA replicates, so does the viral DNA. The viral DNA is doing anything, but it is there. So if the other DNA replicates, so does the viral DNA. It's part of it. So essentially, you're going to end up with all the cells sooner or later having viral DNA. Because you only replicate DNA if you're making new cells. Yeah. No. No. The viral DNA, again, is just simply escape. I mean, don't worry about the repressor proteins. Just the viral DNA is dormant, sleeping, hibernating, whatever. But obviously, sooner or later, it will wake up. So eventually, something spontaneous activates the viral DNA. Now, there's an obvious question. What activates the DNA? What wakes it up? There's an obvious answer. I don't know. It could be a variety of things. It might be that you get sick with something else, and the addition of some other illness wakes up the viral DNA. It might be some chemical contamination of some sort, pollution, where you get exposed to something. Smoking often does it because that's a contaminant, basically. Maybe a physical accident, you fall down the stairs or something, and the physical trauma might wake it up. And sometimes it's just bad luck. Sometimes it's been there for a while, time to wake up. So there's not always a cause at all. So as you can tell, I'm giving very vague answers because there is no one specific cause. But it could be one of many things. And once it wakes up, then the lytic cycle continues. So basically, to be more specific here, lysogenic, you're going to have your attachment, you're going to have your penetration, because the DNA has to get in. But after penetration occurs, the viral DNA is in there, it joins the host DNA, and then it goes to sleep. So it goes to sleep after penetration, but before biosynthesis. And then when it wakes up, then the host DNA gets deactivated. See, now you're doing the lytic cycle. Then the host DNA gets deactivated. You start biosynthesis with the viral DNA. you do your maturation, you do your release. So it is the same stages, same everything, other than the dormant part of it. And then the Leidig cycle, well, did he get sick? Now there's one disease in particular that's famous for this. What do you think? Not mono, pardon me? HIV.
HIV or SV?
What's HSV? Oh, that could do it too, yeah, HSV. You're right, herpes can
Like
do it too.
cold sore.
Herpes can do it too, yeah, yeah. I was thinking HIV. So, sometimes when you get an idea in your head, if somebody says something else, then you don't even know what they're talking about. But herpes would be another example. But I was thinking HIV. Because, average, you may not know this, well, everybody knows that when you're infected, there's always going to be quite a long lag time before you start showing symptoms. The lag time is 10 years on average, so you get infected, and most people think that when you're infected, there are no symptoms. Actually, there are, but they're not recognized. Basically, when you're first infected with HIV, you come down with flu symptoms, or at least it seems like flu. So you get the swollen lymph nodes and your muscles hurt, this kind of thing. And then after a couple of days, it goes away, and you basically think you had the flu. And no, you didn't. You were infected by HIV. And of course, now, the next time you guys come down with flu, you'll start wondering if it's HIV. No, it's probably flu. It probably is. But all I'm really saying is that, in fact, there are some symptoms when you're first infected, but then it goes away, and you live a completely normal life for a long, long time. Again, average is 10 years. So that's good and bad. The good is, of course, you're still living a quality life for a long time. The bad is that even very honorable, normal people, you don't know you have it. So you could very easily spread it to other people. So you're doing your kind of normal stuff, not knowing that you're spreading it. That's the danger of the lysogenic cycle, because you don't even know you got it for a long time. That's how it spreads. Because most people, we've all been reading about this hospital worker in Colorado who spread it probably to a lot of people. But most people would not deliberately do such a thing. But again, you can go 10 years and not even know it. So at any rate, again, the lysogenic cycle is the Leidig cycle, except the dormant period kind of in the middle of it. Lysogeny, that's the word, lysogeny. The condition of having a lysogenic virus. So 3 results. The first one is stupid beyond belief. Lysogenic host cells are immune to reinfection by the same virus. Now I say it's stupid beyond belief because, for example, if you've been infected by HIV, you are now safe from being reinfected. You won't get infected twice. Well, big deal. You're already infected. So who cares if you don't get sick twice? So that's really stupid. What's even more stupid is, yes, you won't be reinfected by the same virus, but you can still catch a cold or still catch the flu. In other words, you can still get other viruses. You're only protected from the virus that you've already been infected from. So, it's stupid. The host cells may develop new properties. We're actually going to talk about that in a little bit because that's actually quite significant. The idea is you're changing the genetic makeup of the cell. You're putting in new DNA. And by putting in new DNA, you're separating some strands of the old DNA. Now, maybe it does nothing, but the fact that you're changing the genetic makeup, it can cause new properties. The new properties might be nothing, and it might actually cause something. We're going to talk about that in a little bit. But the idea is you're changing the DNA. At that point, who knows what's going to happen? Maybe nothing, and maybe something. The third one here, transduction may occur. Okay, nobody knows what that is. But let me take you back in time where I gave you my normally brilliant lecture about why all the bacteria on Earth are dead. And remember, it was because when bacteria reproduce, there's no is asexual reproduction. There's no genetic diversity, that the DNA of the daughter cell is identical to the mother cell, to the parent cell. And what was I going to say? So they're all clones. And the problem with that, of course, is that in case of environmental change, which there always is, that some members of the species will survive, but many members will die out. They cannot survive the environmental change. So on that basis, all the bacteria should be dead. Of course, they're not dead. And we found out one mechanism for achieving genetic diversity. Remember what that was? This is from a while ago.
I have it in my notes.
Somebody's cheating. The question is, what was the technique or the mechanism we discussed earlier?
Conjugation.
Ooh, good for you. She saved all of you.
Conjugation.
Conjugation. That was very good. The conjugation was the F pilus, remember, or the F plasmid forming the pilus, that tube, and the DNA would go from one bacteria to the next. That was conjugation, and that was the mechanism we talked about by which bacteria can get genetic diversity. Well, there's a second mechanism, transduction.
That was your big thing.
What?
That's your big thing.
But my good one, but not so good anymore. Time for me again. Occurs with lysogenic infections. And what the deal is, remember that the the viral DNA is deactivating the host DNA. Now, it's not going to be immediate, but it will occur sooner or later. And then you start transcription of the viral DNA. Well, the point is, and you've heard me say it before, nothing's ever perfect. In this case, it might well be that some pieces of the host DNA might be included in the transcription. They're not supposed to be. It's supposed to be inactive. But sometimes some pieces of the host DNA are included along with the viral DNA for transcription. So then you start making the viral proteins, which will include a little bit of bacterial protein from the bacterial DNA. So those will be included in making the new virus. They will go off and infect other cells, and in doing that, we'll take along some of the bacterial DNA. That's transduction. It's a little bit like when a mosquito bites you, sucks out some of your blood, and then goes and bites somebody else, and squirts the blood into that person. That's how people get malaria. At any rate, the transduction is very similar. The virus is like a mosquito. It's kind of picking up a piece of the bacterial DNA along with its own DNA, along with the viral DNA. And then when it makes a new virus, the bacterial DNA is included. And when it goes off and infects a new cell,
During protein synthesis, it absorbs the bacterial DNA.
it will. And the bacterial DNA will help it make new proteins. But this time, it'll be a little piece of bacterial protein from the bacterial DNA along with the viral proteins.
But it's just using it as building blocks.
Well, it's not so much as being used. That's too strong a term. It's not really being used, it's just along for the ride.
It's like just being stored.
It's accidental.
That's accidental.
Yeah, it's accidental. Yeah, it's not on purpose. And that's why I say it's not so much being used per se, it just happens. And again, my comment, nothing's perfect. In a perfect world, so to speak, there would be no bacterial DNA included. All the bacterial DNA would be inactive, deactivated, and it would not be included. In the real world, sometimes some bacterial DNA is included. And therefore, it gets spread to other cells, and therefore transduction. There is one more mechanism, I was going to say mechanism for genetic diversity. Mechanism for genetic diversity. So conjugation, transduction. The third one is transformation. Transformation. Transformation, well, everybody knows that when things decompose, with death and everything, things decompose. Many times it's bacteria that are helping with the decomposition. They're helping to eat up things and so on. Well, when bacteria do that, sometimes they will actually absorb the DNA that they're eating, and then they'll keep the DNA, they'll use it. So by taking in new DNA, they're going to get new properties. And that's genetic diversity. It would be very, very much the same thing if we were to eat a hamburger and then start moving like a cow, because we were using the DNA. Of course, we don't do that. But bacteria can, sometimes, not all, sometimes. So these are all three are mechanisms for genetic diversity. The transduction is the only one for lysogeny. The other two are just simply other mechanisms, other techniques. Yeah? Anything could. Yeah, why not? Yeah, no, anything could. Yeah. So any questions on the lytic cycle or lysogenic cycle? Again, they're basically similar, except for the dormant part of the the lysogenic cycle. Everybody okay? Okay. Now,